And we're going to be looking now at sample problem 13.7. So sample 13.7, we're looking at on the left-hand side here, the mechanism that we see, that's a series of pulleys, but it says we have a dumb waiter, which is right here in the middle. And they're calling it D. It's and its load have a combined weight of 600 pounds, while the counterweight C over on the left-hand side weighs 800 pounds. We want to determine the power delivered by the electric motor. So you're going to see there's an electric motor here that goes up over, it has a cable that goes up and over our pulley, and it connects to that dumbwaiter. So we want to know what is the power delivered by the by the electric motor when the dumbwaiter A is moving up at a constant speed of 8 feet per second, and B, when it has an instantaneous velocity of 8 feet per second and an acceleration of 2.5 feet per second squared, both directed upwards. So essentially, we're going to be solving this problem twice. The first under the conditions under A, and the second is going to be under the conditions of B. Now, we're asked to find power. If we look back at our equation sheet, we wrote down that power is equal to work over time, or we can also write it force times velocity. And this is going to be the form that we're going to see here in this problem. We're given a velocity and we need to find a force. Now, if we look back at our PowerPoint presentations, now that we have some options here, go up a little bit, you're going to notice that this helps us. I really like this slide because it helps us to decide what avenue we're going to take to do the solution. So in this case, we're trying to find a force, okay? We're given acceleration, we're given velocity, and we're not interested in displacement. So we're going to work with Newton's law, second law again. We're not going to do the work energy theorem this time, okay? So, so we're going to be back over, if you would, on the left-hand side here, working with Newton's second law on this last sample problem. So what we're going to do is I am going to go underneath and we're going to get started on our sample problem. So as we normally do, we're going to start with what we're given and what we're going to try to find. So we know that the weight of the dumbwaiter is 600 pounds. And then we know that the weight of the counterweight is 800 pounds. So D is the dumbwaiter, that middle weight, if you would, and C is the counterweight on the outside. Do you guys know what a dumbwaiter is?
Really bad waiter.
No, it's not a really bad waiter. It's yes, it's a little house elevator that I guess in years gone by, they used to have between floors, they would have this little manual elevator system that would be a series of pulleys and such. And that's kind of what this is. Yes.
They have one at the gingerbread.
Oh, do they? They also have one. Have you ever gone to the Pabst Mansion?
Yep.
They have one there too that they show you. So anyway, that's what a dumbwaiter is. So we are going to try to find, okay, we're going to try to find power delivered by the motor under two conditions, okay? A, it's going to be moving at 8 feet per second, and that's going to be the velocity of the dumbwaiter, velocity of D, and it's going to be going up, okay? And it's going at a constant velocity, so the acceleration is 0 in condition A or in part A. Part B, we're going to have an acceleration equal to 2.5 feet per second squared and an instantaneous velocity of D at 8 feet per second, and both are going up. So in this case, we do have an acceleration, okay? Now, because we want to try to find power, right? P is equal to F times V, okay? And our V is going to be equal to the velocity of that dumbwaiter, okay? And we'll see why in a second. I'm gonna look back at the illustration. Remember, we want the power that's exerted by the motor. And if we look here, the right-hand cable is the one that's going to the motor. So the velocity is D is the velocity that we're interested in because that's going to be the force that's coming off of that motor. Okay. So I'm just going to put here, P is equal to power. F is going to be equal to the force on the cable from the motor. And then V is equal to VB, the velocity of that block D or that weight D. Okay. So looking at part A first, okay, we know that our velocity of D is going to be equal to 8 feet per second going up, and it's uniform, so no acceleration. And if you want to write that, that way it kind of gives you a hint at why we're doing what. So as we said earlier, we're going to use Newton's second law this time. So we're going to kind of go back to our previous unit, and we're going to draw our two versions. And this is going to be I'm going to do, wait a second here. Let me look at my notes. Yeah. Okay. So we'll do body C first, and then we'll do body D. So I think I can leave it where I'm at. So we are going to do 800 pounds. Okay. Now, if we look back at the illustration, we're looking at C here. I'm going to zoom in a little bit. Okay. So we're looking at C. So C is going to have a weight going down of 800 pounds. And then you'll notice there's a little cable here, but connected to it are two sides of that pulley. So that means that there's actually two reactions going up, which is going to be equal to the tension in the cable that's going to connect over here to D. So what we're going to do is we're going to simulate that as actually two separate forces, a T and a T. We're going to call that the tension in the cables. Put those on the side here, T and T. So we basically have two T's going up that are going to have the same tension. Okay. And we're going to say that's going to be equal to, okay. And now let's relook at the mechanism, okay? So we know that D is going to be going up, right? So if we look at how this is connected, if D is going up, what's happening to C? It's going down, right? So we're going to actually show the mass and the acceleration going down, right? Because it's going to be moving down. But because there is no acceleration, acceleration is equal to 0, this is actually going to go to 0. So now when we sum our forces in the y direction, instead of saying it's going to be equal to mass times acceleration of c, we're going to say it's equal to 0. Okay. So now we've got two t's going up, so we can say 2t minus 800 pounds is equal to 0, our normal convention. So then when we solve for t here, we're going to put the 800 on the other side. 2t is equal to 800 pounds. So t is equal to 400 pounds. Okay, so that's going to be the tension in the cable. So I'm going to put my little cloud around there. It's not a final answer, but it's one that's probably going to come in handy. Now we're going to do the very same thing for body D. Okay, body D. Okay. So kind of the same thing, but we're going to have a little bit different connections. So we know that the weight is 600 pounds for our dumbwaiter up here. Okay. And if we look back at our illustration, okay, on the right-hand side, this is going to be the force going to the cable. We're going to call that F. Okay, so that's consistent with what we have in our power equation. And then T is the tension that goes over to C. So we're going to have T on the left-hand side, and we're going to have F on the right-hand side. Okay, so that means we're going to have T here, and we're going to have F over here. All right, so F is going to the motor, T is going to the weight C. Now, we already know what T is, right? So we'll be able to fill that in. And then we're going to have the other side here is going to be, D is going to be moving up, okay? So that means that we would show MD and AD. Now, again, we know that this is going at a uniform velocity, no acceleration. So this actually goes to 0 as well. So now we can do the very same thing. We can sum our forces in the y equal 0. And now we can say we have T over here, which we know to be 400 pounds. That's a positive value, plus F minus 600 is equal to 0. So 400 minus 200, so it's going to be F minus 200 pounds is equal to 0. Putting it to the other side, F is equal to 200 pounds. So then, there we go. Now, we're not done, right? We're not done because now at this, we need to know what the power is delivered by the motor. So now that we know what the force is, because we needed F, we can now calculate the power. Okay, so P is equal to F times V. Scooch that down. So now we know that F is 200 times a velocity of 8 feet per second. So my power is going to be equal to 1,600. Now this is going to be pounds, feet per second, okay? Those aren't standard English units for horsepower. So we need to do our converting of our horsepower. So if you remember, I gave you that conversion on our sheet, and that's going to be, I'm going to do a conversion of 550, sorry. And this is pound feet per second. So it cancels out the whole thing is equal to 1 horsepower. Oopsie. 1 horsepower. So our P, let me know what you get for a value in horsepower when we're going at a constant rate of 8 feet per second. What is it? 2.91. Yep, that sounds correct. Horsepower. Okay, and that's the answer for part A. Okay. Any questions at all on that first part? Okay, so we're gonna use this very same problem again, but this time we're given an actual value of acceleration and then the same velocity of 8 feet per second, and both of those are going to be going up. So we are going to start a new page here, and now we're going to do the second part, part B. And this is, we have an acceleration equal to 2.5 feet per second squared going up, and velocity D of 8 feet per second also going up. Now, the other thing that we need to recognize here is that if we look back at our illustration, so if we move up with D, okay, it's connected through this cable right here, okay? Well, how would you describe the distance traveled D to C? So for instance, what is the relationship of how far that C travels to D? So if D goes 1 unit, how far will C go? Half or 2 or the same? It's going to be half, right? Yeah. So what we can say is we can say that XC is equal to half of XD, or it's not really X because it's vertical, but you know what I'm saying. It's just a distance. So we could do Y's. We could do Y's. That's maybe the better way to do it. I did it X just for distance. Okay. So the displacement in the Y direction of C is going to be half the amount of D. So with that, we can also say that the acceleration at C is going to be half the acceleration at D, right? So if that's the case, we can say it's going to be half of 2.5 feet per second squared, right? So our AC is going to be 1.25 feet per second squared, and it's going to be going down, okay? Because that's the direction that it's moving. All right. Okay. So now we're going to be looking at body C and body D, just like we did on the previous, all right? Because we need to get to what is that force again that's at the motor. All right, so looking at body C, okay, we are going to identify on body C that going down is going to be positive because that's its normal direction. So even though we say up is positive, in the application of the motion that's occurring, when D goes up, C goes down. So C is going to have a positive going down, but D is going to go back to positive being up, okay? And it's just because of the way the operation is occurring. Okay. So we'll do our body C. We know that this is going to be the two T's, right? And we have 800 pounds going down. It's going to be equal to, now this one is also going down. So it's going to be mass C times the acceleration of C, right? So now, when we sum our forces in the Y equal to mass C times acceleration C, we're going to have something on that right-hand side now because there is acceleration. So let's sum our forces first. We're going to have the same 2T minus 800 pounds is going to be equal to the mass at C. We know this to be 800 pounds, so we have to take 800 divided by 32.2 times the acceleration, which we determined was 1.25. Okay. So solving for T here, okay? I'll let you go ahead and solve for T. Oh, you know what, Lex, I see your question. Yes, this would be positive, this would be negative, but we'll end up still with positive values in the end. So in the end, the value doesn't change, but you're correct. Thank you for catching that. So Lex remembered, or she brought to my attention, negative 2T because it's going up, because our convention is positive going down. And then we would have a positive 800. The signs still come out in the end. Again, the values will remain the same, but this is the correct way to do it according to our convention. Thank you. So what do you guys get for T? Yep, 384.5, and that's going to be pounds. Okay. So now that's the tension in the cable that goes from the left-hand side of D to and through our weight C. Okay, now we're going to do the very same thing, and we're going to look at body D, our dumbwaiter. Okay, now this time, because the direction of motion is going up, we're going to go back to a positive direction going up. Okay, kind of back to the normal, if you would. So this is going to be D. 600 is D. 600 pounds. And then we have force F and we have force T, which we know to be 384.5 this time. Going to be equal to, now this one is going up, so it's going to be mass D times acceleration D. And that was the acceleration we were given at the start of the problem. So doing our sum of our forces in the Y equals MDAD. We're going to have positive 384.5 pounds plus F minus 600. You don't have to put the units in. I'm just doing it out of habit, sorry. And then we're going to have 600 divided by 32.2, which is gravity, times 2.5. So our only unknown here is going to be our F. So go ahead and solve for F. Let me know what you get for F. What did you get? I got something different. 262.1. Is that what you got? 262.1. Yep, that's what I got. Try it again, James. 262.6. Okay, we're really close. Probably a little bit of rounding-ish, right? So good, good. All right, now we have our force that we can use in our power equation. So the last step is to calculate the power. Okay, so P is equal to F times V. We just calculated that value of the force F, so 262.1. That's what I'm going to use. If you have a different decimal, you can use your decimal. I'm sure we'll still be pretty close. And then we have 8 for our velocity. Okay. I'm going to put the units in here just to verify. And this is feet per second. So our power should come out to be 2096.7. Okay. And that's going to be pound-feet per second. Then we want to convert that 550 pound-feet per second is 1 horsepower. So these cancel, and you should get about 3.81 horsepower. Double check my numbers just to be sure, or make sure that you can get that same number. Okay. All right. Now, as we look at this, remember, we did this 2 different ways. The first way we were looking at it, we wanted to know what the power was when it was moving at 8 feet per second at a uniform velocity or a constant velocity, no acceleration. And the value we got for our power was 2.91, okay? The second way that we did it is we had an acceleration when it hit that 8 feet per second, and we have a power of 381 horsepower. How do you feel about that number being larger for the second set of conditions than the first set of conditions? Pretty much by a full horsepower. Does it make sense? Why does it make sense, Josh? Yes, the acceleration is what makes the big difference here, okay? So whenever we are dealing with accelerations, there's like more to the problem. It's like it takes more out of it. So just like when you're, driving in your car and you're going at a constant speed of 60 miles per hour, it doesn't feel like anything's going on. But if you have to accelerate and exert power in order to get from 0 to 60, you feel a very big difference, right? It's working a lot harder. So acceleration is something that when we have things that are moving, dynamic, accelerations now are things that we have to deal with and be aware that we're going to need more to do the work. So power is going to be higher in this case. All right. Then that's our last problem that I have planned as far as sample problems for this section. So you would be prepared to start looking at now the application problems, which we'll look at next.